Okay, well, to pick up today where we left off last time, we were talking about, well, the section that we were on is called formal charges and resonance. Last time we got to the formal charges, but we didn't get to the resonance. Formal charge, just a quick review, is sort of a hypothetical bookkeeping device where we assign a hypothetical charge to the atoms in a molecule or a polyatomic ion, and it's one way of keeping track of electrons, and it's also a way of deciding which possible structure is the best for a molecule or an ion if there's more than one plausible Lewis structure. Because sometimes, every once in a while, even if you follow the rules for drawing Lewis structures to the letter, you can still end up with more than one possibility for the Lewis structure. And formal charges are a good way to decide between them. We saw the example of SiO2 last time, where and you generally want the formal charges to be generally as close to zero as possible. If there has to be a negative charge, then it needs to be on the most electronegative atom in the structure, and positive charges should generally be on the less electronegative atoms in the structure. And all of the formal charges on all of the atoms in the structure should add up to the total charge on the structure. So if it's a neutral molecule like SiO2, the total of all the formal charges on the silicon and the two oxygens should be zero. And the way you calculate the formal charge for a given atom in a molecule or a polyatomic ion is you take the normal number of valence electrons that that element has, minus all of the lone pair electrons on that atom in the Lewis structure that you've drawn, minus 1/2 of the bonding electrons. So remember, each bond consists of 2 electrons. So essentially, you're subtracting here the number of bonds that that atom is engaged in, or 1/2 of the number of electrons in all of the bonds around that atom. And that will give you your formal charge. And we decided for silicon dioxide that the first structure, where silicon has a double bond to each oxygen, is the best one, because that's the one where all of the formal charges are zero. Okay, so moving on to resonance. Resonance is the kind of situation that you have when you have two or more bonds in an atom between the central atom and the same outer atoms, and the Lewis structure ends up giving you basically a single bond for one and a double bond for the other, or maybe a single bond for one and a triple bond for the other, or maybe a double and a triple, or something like that. And what happens in such a situation is that you can draw the Lewis structure like that, but in real life, the valence electrons are often delocalized. That's what we call it, because of the way the orbitals in the atoms are structured. You often have things like empty p or d orbitals, where the valence electrons involved in the bonds between the central atom and the outer atoms can actually spread out, and you can actually have electrons that are sort of spread out over more than one bond, and that's known as resonance. An example of resonance might be the structure for the nitrite ion, NO2 minus. One Lewis structure you could draw would be like so, with the nitrogen in the center, and nitrogen is definitely in the center. There's no doubt about that. The formal charges prove that. And the nitrogen would then have a double bond to one oxygen and a single bond to the other oxygen. But which oxygen will have the double bond and which oxygen will have the single bond? It could go either way. And I've drawn it both ways here. And those two structures are equivalent to each other. But if you had a situation where one of the oxygens has a double bond and the other one has a single bond, you would expect the nitrogen-oxygen double bond to be both shorter and stronger than the nitrogen-oxygen single bond, because that's the way how bonds work. Generally, triple bonds are shorter than double bonds are shorter than single bonds, And also triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. So this bond here should be shorter and stronger than this bond here. That's actually not the case. In real life, both of the bonds in the nitrite ion are of equal length and equal strength. And the reason is resonance. And it's not even a case where you've got the structure flipping back and forth quickly between one form and the other. So maybe it goes, double bond on the left and it flips to double bond on the right, left, right, left, right, left, right really fast. No, that's not it, actually, because they have ways of slowing down that transition and measuring the bond lengths and strengths, before it can change. And they're still the same length and still the same strength. What's really going on is that the actual structure is a resonance hybrid. These two individual structures here, where one side has a double bond and one side has a single bond, are known as resonance forms. But the real structure is actually a hybrid between those two forms. And it turns out the electrons in the double bond are actually spread out between the nitrogen and both oxygens. And the way we usually draw that is by having a single bond and then like a dotted line above it to represent the partial double bond. So actually what you've got in terms of length and strength is the nitrogen-oxygen double bonds, both of them in the nitrite ion, are essentially halfway between single and double bond status. Okay, and they're that way all the time. And so this would actually be a better way of drawing the Lewis structure for the NO2 minus ion than what we had up at the top of the page. Another example could be the nitrate ion, NO3 minus. When you draw that, you've actually got 3 oxygens, and one of them in the Lewis structure will end up having a double bond, and 2 of them will be single bonded. But you could draw it with the, of course, being a Lewis structure, you could draw it any number of different ways. But the way I've drawn it here, I've drawn 1 oxygen to the left, 1 oxygen to the right, and 1 oxygen above the nitrogen. And so I could draw this with the double bond between the nitrogen and the oxygen on the right, or the double bond between the nitrogen and the oxygen above it, or the double bond between the nitrogen and the oxygen to the left of it. Those are 3 resonance forms for the nitrate ion. And the number of resonance forms a structure can have will really depend on the structure itself. Basically, how many identical atoms you have bonded to the central atom and how many multiple bonds are involved too. So in this case, nitrate ion actually has 3 resonance forms, and the resonance hybrid, the way that the nitrogen or nitrate ion would really exist, would be something like this: nitrogen with a single bond to each of the oxygens, but then a dotted line between from oxygen to oxygen, representing the partial double bond that can move around. Or that, and like I shouldn't even say that it doesn't actually move around, it's spread out. Those extra electrons from the double bond are just spread out between the nitrogen and all 3 oxygens. And in the nitrate ion, you've got 3 nitrogen-oxygen bonds that are all the same length and the same strength. And so that's just a quick introduction to resonance. The next thing we want to look at is section 7.5, and that is strength of ionic and covalent bonds. And we know that bonds between different elements will have different strengths. Well, we haven't really proven it yet, but it makes sense that they would, because different elements have different electronegativities, which means different elements have different levels of attraction for electrons, which would tend to indicate that different atoms will essentially hold on to each other with different levels of strength, and that is actually true. We can measure the bond strength as the amount of energy released when a bond forms, or we can measure the amount of energy input required to break a bond. And in practice, what we usually go with is bond dissociation energy, or capital D. And capital D, or bond dissociation energy, is what I've underlined here, the amount of energy input required to break a bond. It's because that's easier to measure. And so the bond dissociation energy is the energy required, and it's always endothermic. You always have to put energy in to break a bond, no matter how weak it is. The bond forms for a reason, and so it's not going to want to be broken unless you put some force into it. So energy is required to break a bond between two specific atoms in the gas phase, and that is the bond dissociation energy. The units for bond dissociation energy are usually given either as kilojoules per mole. That's what it's usually given as in tables. But in cases where you have a reaction written out, it's often given as just kilojoules for whatever amounts are involved in the reaction as it's written. So for a diatomic molecule XY, that is, involving element X and element Y, X is just sort of a generic symbol for an element if you don't want to specify what it is, as is Y in this case. Actually, there is an element that has the symbol of Y, but it's not a very commonly encountered one. So XY is just a hypothetical diatomic compound in the gas phase. And if you break that bond and separate it into X in the gas phase plus Y in the gas phase, the enthalpy for that reaction is the bond dissociation energy of the XY bond. Okay. An example in real life might be, say, hydrogen, H2. That consists of two hydrogen atoms with a bond between them. And if you break that bond and turn the H2 into 2H in the gas phase, then the enthalpy for that reaction would be the bond dissociation energy of the hydrogen-hydrogen bond, and that is positive 436 kilojoules for this reaction as it's written. Since this reaction is written for 1 mole of hydrogen, then this could also be considered 436 kilojoules per mole for the dissociation energy for the HH bond. Another reaction could be something like taking methane, CH4, and breaking all of its bonds. Methane has a Lewis structure where you have carbon in the middle and a single bond to each of the hydrogens around it. So for 1 molecule of methane, you've actually got 4 carbon-hydrogen bonds. So this equation involves separating CH4 into carbon in the gas phase plus 4 hydrogen atoms in the gas phase. And the enthalpy change for this reaction is 1,660 kilojoules. And what that means is that the bond dissociation energy for the carbon-hydrogen single bond would be that number divided by 4, because there are 4 carbon-hydrogen single bonds in the 1 methane. And so the bond dissociation energy for the carbon-hydrogen single bond would be 415 kilojoules. That's on average, because even though all 4 of these carbon-hydrogen bonds are exactly the same, and it doesn't really matter which one you break first, the thing is that once you break one of them, it's actually easier to break the next one. And so the bond dissociation energy starts out as highest for the first hydrogen you take off, but then it gets lower for the ones after that. And so the values that you see listed in tables for bond dissociation energies are average values. And that's why when we find the enthalpy change for an overall reaction using bond dissociation energies, the numbers are only really approximate. They're not exact, because the bond dissociation energies listed are averages. Sometimes in the case like hydrogen, if you're breaking multiple bonds of the same type, the first one might be hardest, but then the next one might be easier. So the actual numbers can change, and it depends on how many of the bonds you break. If we break all of the carbon-hydrogen bonds present, then 415 should be a pretty accurate number. But if we only break one of them, then 415 kilojoules would actually be fairly low, because it takes more than that to break the first one. Also, there are cases where the atoms on either side of the atoms involved in the bond can have an effect on the exact bond energies also. And so the numbers in the tables don't take that into account either. Relative strengths of covalent bonds can be classified according to the type of covalent bond it is. Well, generally, first of all, polar covalent bonds are generally more stronger than non-polar covalent bonds, but also triple bonds are are stronger than double bonds, and double bonds are stronger than single bonds. And in terms of length, the stronger it is, the shorter it is. And so triple bonds are shorter than double bonds are shorter than single bonds. Single bonds are the longest, triple bonds are the shortest. There's a table on page 368, 378 that gives you average bond strengths, and you can use that table for looking up the numbers for when when you encounter homework problems that involve finding enthalpies of reactions from bond dissociation energies. And the table after that on page 369 or 379 gives bond strength versus the length, and it puts actual numbers on them. I've shown you the trends up here, but the table gives actual numbers for that kind of thing, if you're interested in seeing exactly how much it changes. Using bond strength to estimate enthalpy change for a reaction, and as I mentioned, when finding enthalpy through bond dissociation energies, you generally only get a fairly approximate number because we're using average bond energies, and bond energies in specific cases may be a little higher or lower. And the way we do this is we assume that all of the bonds in the reactants are broken and all of the bonds in the products are formed during the reaction. And as I said, this is not as accurate as using enthalpies of formation to find enthalpy changes during reactions. But it's not always easy to find enthalpy of formation information for some things. So this is an alternative. So the delta H, or enthalpy change of the reaction, is going to be just the total of all of the bond enthalpies for the bonds broken, or in other words, the bonds involved in the reactants, and minus the total, that is the summation, of all of the bond dissociation energies for the bonds formed. In other words, the bonds in the products. The book left out the little n's there because I don't know why, but the reason that you need the n in there is n is the number of moles of each bond involved in the reaction. And the bond dissociation energies are given in kilojoules per mole. So you definitely need to multiply each of them by the number of moles of that particular bond involved in the reaction. And a good example of that would be the combustion of methane. If you take CH4 and burn it in air, each mole of CH4 methane will combine with 2 moles of oxygen and will produce 1 mole of carbon dioxide gas and 2 moles of H2O gas. You can draw Lewis structures, and actually for cases like this where you're using bond dissociation energies, you kind of have to draw the Lewis structures for the reactants and products, because you need to know, for one thing, how many bonds of each type there are, and also you need to know whether those bonds are single bonds or double bonds or triple bonds. So for CH4, we saw that before a few minutes ago. It's just carbon with a single bond to each hydrogen. So we know that among the bonds broken will be 4 carbon-hydrogen single bonds for the methane. Oxygen, each oxygen molecule has an oxygen-oxygen double bond. So this is why you need to do the Lewis structures. Unless you just remember that off the top of your head, you'll need to know that this is a double bond here, because the tables also list values for oxygen-oxygen single bonds. And some tables might even have values for oxygen-oxygen double bonds. I don't know. Ours doesn't, I don't think. But anyway, you've got 2 oxygen-oxygen double bonds among the bonds being broken. For the bonds being formed, again, you need to know that in carbon dioxide, you have 2 carbon-oxygen double bonds, because their tables also list values for carbon-oxygen single bonds. So you want to be sure you're getting carbon-oxygen double bonds. So among the bonds formed would be 2 carbon-oxygen double bonds. And then we have two water molecules, and each of them contains two hydrogen-oxygen single bonds. And so two bonds in each molecule, two molecules means four hydrogen-oxygen single bonds. And so then you go to the table and look, well, you can set up your equation first and then look the numbers up. Delta H for the reaction is going to be 4 times the dissociation energy of the carbon-hydrogen single bond, plus 2 times the dissociation energy of the oxygen-oxygen double bond, minus the quantity 2 times the dissociation energy of the carbon-oxygen double bond, plus 4 times the dissociation energy of the hydrogen-oxygen single bond, close parentheses. And when you look up the numbers, that's going to be 4 times 415, because that's the dissociation energy for the carbon-hydrogen single bond, plus 2 times 498. That's the dissociation energy for the oxygen-oxygen double bond, minus 2 times 741 plus 4 times 464. And all of that works out to negative 682 kilojoules per mole. It's negative, so that means the reaction is exothermic, and that's good because burning methane is definitely exothermic. Methane is the principal component in natural gas. So yeah, that kind of gives off more energy than it takes in. Interestingly, when you do that same reaction and find the enthalpy for that reaction using enthalpies of formation, you end up with negative 802.5 kilojoules per mole, which is fairly different. I mean, it's not hugely different, but it's different enough that, again, a reminder is in order that using bond dissociation energies only gives you the approximate delta H for the reaction. And, it's not all that far off. The number we got from bond dissociation energies is almost 700. The actual number is just barely over 800. So yeah, it could be worse. Another example could be the synthesis of ethanol by combining ethylene with water. And from that, you get ethanol, which has the formula C2H5OH. So what happens here is that basically the oxygen or the hydrogen-oxygen bond splits off, and the hydrogen goes to one side of this double bond, and the OH goes to the other side of the double bond. So you're basically literally adding water to the ethylene molecule, and you get ethanol, C2H5OH. Again, you need to do Lewis structures for these reactions unless you know what the structure of the molecule is like off the top of your head, or unless you can conveniently look it up somewhere, because you need to know how many and what types of bonds are broken. So if we have 1 mole of ethylene plus 1 mole of water yields 1 mole of ethanol, and we can see among the reactants, we're going to end up having to break 1 mole of carbon-carbon double bonds, right there, 4 moles of carbon-hydrogen single bonds, and 2 moles of oxygen-hydrogen single bonds. Then among the bonds formed, we're going to have 1 mole of carbon-carbon single bonds, right there, 5 moles of carbon-hydrogen single bonds, 1, 2, 3, 4, 5, 1 mole of carbon-oxygen single bonds, and 1 mole of oxygen-hydrogen single bonds, right there. So essentially, you're just adding up all the numbers of all of the different types of bonds in the product. So when we work that out, it's going to be basically 1 times the dissociation energy of the carbon-carbon single bond plus 4 times the dissociation energy of the CH single bond. Oh, did I say carbon-carbon double bond here? Plus 2 times the 2 times the dissociation energy of the oxygen-hydrogen double bond or single bond, minus 1 times the dissociation energy of the carbon-carbon single bond, plus 5 times the dissociation energy of the carbon-hydrogen single bond, and so on and so on. You can see the rest. Anyway, that works out to negative 35 kilojoules per mole. If you do that using enthalpies of formation, you get negative 45.4. So, again, not too far off, but again, using bond dissociation energies, it's really an approximation more than anything else. That brings us to ionic bond strengths and lattice energies. And we seem to be right at the 25-minute mark right now, so I think I'll cut here and come back with that at the beginning of part B.